with your 22,000 H100s, you could reach GPT-4 scale compute in 5 days. They tried introducing a sandbox flag into the code to be improved. Sure enough, the improver would do things like remove the sandbox flag. And I don't want to anthropomorphize this too much, but you can imagine a human doing this. And I don't really know what that sandbox flag does, but it's probably slowing me down.
Hello, and welcome to the Cognitive Revolution, where we interview visionary researchers, entrepreneurs, and builders working on the frontier of artificial intelligence. Each week, we'll explore their revolutionary ideas, and together we'll build a picture of how AI technology will transform work, life, and society in the coming years. I'm Nathan Lebenz, joined by my co-host, Eric Tornberg.
I think in general, the writers were very happy with where the deal landed. On the AI stuff, it seemed like it ended up around where it was the month before, maybe with a more probably complete, fleshed out legal understanding that the studios can't use generative AI to cut out writers out of credit or to turn their first drafts into second drafts. But on training on our scripts, I think the final phrase they told us is that we retain our right to assert our rights relative to it. So I think we got nothing on the training. And the argument from the studios, we were told, is they were like, well, OpenAI and all these other companies are training on your scripts. So, how can you ask us to agree not to? But some sense that I think the guild might try arbitration or other venues to try to, stake out some rights to us. But I think that's all pretty unclear how that's going to go.
Let's get to it then. So I think today I'm kind of thinking of structuring this as the future of the transformer. I was listening to Last Week in AI, and Jeremy, who's one of the co-hosts there, who I'm a big fan of, threw out this number that the H100 does, he said 100 trillion operations per second. I'm not super well versed in this, in all the details, because there's a lot of little precision points on the definitions. And then, I think it all kind of gets washed away when you start to put these H100s into clusters. And then it's you kind of have a theoretical max of what the machines can do, but then you also have to engineer, obviously pretty substantially to get anything close to the theoretical max. So there's some of the research that we're going to touch on today kind of speaks to getting more out of hardware. But for starters, it was first of all, wow, that is an insane number. 100 trillion operations per second. That's unfathomable, right? But then I was also kind of thinking, well, that starts to give an interesting angle on what does it take to train a GPT-4 in today's world? So with the caveat, again, that all these are pretty rough numbers, and I would invite any listeners to give feedback on anything I'm kind of simplifying too much. But GPT-4 is said to be trained on approximately 10 to the 24th flops. 10 to the 24th. And 100 trillion is 10 to the 14th. So I created just a super simple little toy spreadsheet where I was like, all right, let's imagine we have a target scale of how much compute is going to go into a frontier model. And I have it just defaulted to 10 to the 24th to represent approximately GPT-4, even though we don't know exactly what that number is. And then a device flops, which for approximately H100, I'm saying that's 10 to the 14th. That means you have 10 to the 10 seconds of H100 time that you have to run, assuming you're, making full-ish use of it, to have enough flops to train a GPT-4 class model. So then I was just like, okay, well, what does that look like in actual human time? And, it depends on, obviously, how many H100s you have. You can network these things together. But if you have 1,000, then you can get to a GPT-4 class model in, per my little calculator, 115 days. So 1,000 H100s gets you to GPT-4 training scale compute in basically 4 months. Okay, let's say you are an Inflection and you've raised $1.3 billion or whatever, and you've announced your public plans to buy 22,000 H100s and to put those all into one of the world's premier supercomputers, although honestly, I expect that will be eclipsed, before we know it. That would mean with your 22,000 H100s, you could reach GPT-4 scale compute in 5 days. 5 days of the 22,000 unit H100 cluster from Inflection to get to GPT-4 scale training. Pretty decent uncertainty bounds on this. I would say that's probably about as low as it gets. If you have an architecture that's suboptimal in any number of ways, it could take longer. All sorts of things, could take longer. Obviously, you're going to be running experiments at smaller scales. You're not going to be just like maxing out every second on your cluster. But I thought that was a pretty interesting starting point, because for a lot of the things that we're about to talk about, it's going to be like, well, here's this kind of improvement and here's that kind of improvement. And what I think is pretty interesting is like, do all these improvements kind of come together and compound, or are they sort of just fragmented, divergent strands of research? And I think a pretty strong indication that they at least have a decent chance of coming together into the same systems over the next, months to year is just how achievable it's going to start to be to run GPT-4 scale tests. If you have that level of compute and a GPT-4 scale takes you 5 days, then, and by the way, they're talking Gemini supposedly, 5 times bigger or whatever. That's obviously stupid kind of rumors that I don't think are super well defined. But if that is to mean 5 times more compute, it's still under a month for an Inflection scale cluster to hit a Gemini compute scale. Again, a lot of assumptions there, obviously. But the key thing, if you can get down to days to do GPT-4 scale, then you're, at months or a couple months to do the next order of magnitude up. And it really gives you a lot of room to start to experiment with all of these different architectural, algorithmic, training improvements that we'll explore today, and potentially unify them and unify all of these different discoveries, or many of these kind of most impactful different discoveries into a single thing, which I think, as we kind of go through this, it'll start to be, hopefully pretty clear that like, man, there's still a lot of room left for these systems to improve. And again, if one can be cranked out from a single lab on kind of the order of every week, then, there's going to be a lot of opportunity for people to experiment with stuff. And, it really does feel like we're entering the steep part of the S curve at a minimum. I'm not ready to call this a long-term exponential, but it does not feel like we're, slowing down anytime soon. And also, even if it is an S curve, if the top part of the S curve is at a high enough level, then, it still could very easily be a transformative situation, even if there is some kind of plateau that's, short of, let's say, godlike intelligence. It sure seems like, we're not stopping anytime soon. So that's my first thing, just to give a context for how many GPT-4 scale systems we're likely to see generated and, created, even just in the course of experiments, as things are getting so big on the compute side. Those are just, from what I understand, kind of just starting to come online. That's not like a cheap thing, right? I mean, you're probably talking about, getting up into the hundreds of millions, into $1 billion, to buy a compute cluster that big. So it's not the kind of thing that many organizations can do, but it certainly is the kind of thing that dozens, of organizations globally have the resources already to do, or, as we've seen with Inflection, literally just raised it VC to go out and do it. You can do that sort of thing when you're one of the founders of DeepMind. Any thoughts on that before we jump into the research itself?
Yeah, I mean, I think that makes a lot of sense to me, that you might get beyond multiplicative gains from investment and algorithm breakthroughs and the compute, because as you're saying, you can use all this extra compute to run way more experiments and get more efficient algorithmically. I do wonder if you'll get to a place where like right now you can experiment on GPT-2 very cheap, but it's hard to experiment on GPT-4. Will we get to, higher scale models? It'll be interesting to see how effective GPT-4 experiments are at translating to the models that are pushing, whatever the compute levels at the time to their max. Yeah, and one other small thing that seems interesting to what you're saying on experiments is also, it feels like it's a bit of a small self-correcting for any lags in demand or advances. Whatever people, if the demand for the AI services ends up being lower than people expect, that's just more compute to run more experiments and to get the advances that get the demand back up.
Yeah, and the demand is seemingly going pretty strong. I mean, that's not something I don't know if we've talked about that, maybe briefly, but it wasn't long ago that the news hit that OpenAI had gone from, I think it was like something in the mid $20 million of revenue for all of 2022 to hitting $1 billion run rate in maybe August or maybe it was July. I don't know exactly when that hit. And now the latest report is that they're at 1.3 billion in revenue run rate, which means they're doing more than 100 million a month, obviously, which means, they've gone from something like 2 million a month average last year to north of 100 million a month this year. So again, just your classic, 50x revenue growth year over year. But that's, I don't know that that's really almost ever been seen at that scale in, even in the most successful venture stories. Something like Uber, maybe hits that kind of growth trajectory for a minute, but that's obviously extremely rare air and super exponential. So, and I think they're definitely making money on all this stuff. I mean, there's been a lot of speculation about, well, how much does it cost to run and whatever. They've dropped the price pretty aggressively. Rumor has it that there may be another price drop coming on the developer day, coming up on November 6th. Unclear exactly what that will look like, but it certainly seems to be their strategy to drop the prices as much as they can. OpenAI, seems to be reacting to developments in the world and kind of adjusting their release schedule depending on what's happening out there. Like, it seems like they accelerated the release of fine tuning, or at least kind of said, okay, yeah, let's go ahead and ship it once Llama 2 was out. And it was like, well, now anybody can go fine tune that. So we may as well allow them to, fine tune 3.5. They seem to be taking that kind of approach where they're like not going to be behind on any significant dimension for long. So, they have a lot more, I think, still in reserve than we've seen. Certainly, even just fine tuning GPT-4, coming before long would be a big deal. And when you see these kind of training timelines, you're like, geez, if Inflection can do, one of these things, a GPT-4 scale model in a week, that's kind of crazy. What are the biggest, kind of edges that they have to take the air out of that is to lower the price of the top stuff to the point where, well, why would I even bother? And Inflection's going to do what Inflection's going to do. But if I'm, somebody who might just go ahead and be an OpenAI customer, then, the price really does matter, especially if you're thinking about all these agent type of things. And there are a lot of tokens. And the amount of tokens that translates to is just unbelievable. Keeping in mind that 3.5 Turbo is 1 million tokens for $2. So you're like, geez, I've got 500 million units of 1 million tokens. So that's 500 trillion GPT 3.5 Turbo tokens. It's a huge amount. It's also not that much if you think, well, okay, let's divide that by, let's just say 5 billion people. Then, we're talking about 5 orders of magnitude, 5 zeros. So 100,000 tokens per person per year. That's actually not that many. I used 25,000 tokens just to do a little React app feature edition not long ago. And that was a higher level model. So that would be, again, 3.5 tokens. If you bring that in and say it was GPT-4, then you're like, well, it's only 10,000 GPT-4 tokens per person in the world. So there's definitely still a lot of room for way, way more tokens. Some of these use cases probably would require a drop in price. I think they're motivated by the fact that like it's getting so accessible to train pretty big models that they're just like, let's, continue to drive the price as low as we can, eliminate every possible need for anybody else to do that who's not already hell bent on it. What would even be more explosive revenue growth, always good to keep in mind that they're not 100% economically motivated. They've got their returns cap for their investors. They've got, this kind of charter that says like beyond a certain amount of wealth for our stakeholders, then we're going to start to redistribute it. So fascinating strategic dynamics governing that. But I just keep thinking, man, if Inflection can do a GPT-4 scale thing in a week, then, no wonder they're going to release some stuff and start to bring some fine tuning online sooner and, potentially bring us another price drop before we know it as well.
Hey, we'll continue our interview in a moment after a word from our sponsors. If you're a startup founder or executive running a growing business, you know that as you scale, your systems break down and the cracks start to show. If this resonates with you, there are 3 numbers you need to know: 36,000, 25, and 1. 36,000. That's the number of businesses which have upgraded to Netsuite by Oracle. Netsuite is the #1 cloud financial system, streamline accounting, financial management, inventory, HR, and more. 25. NetSuite turns 25 this year. That's 25 years of helping businesses do more with less, close their books in days, not weeks, and drive down costs. 1, because your business is one of a kind, so you get a customized solution for all your KPIs in one efficient system with one source of truth. Manage risk, get reliable forecasts, and improve margins. Everything you need all in one place. Right now, download NetSuite's popular KPI checklist, designed to give you consistently excellent performance, absolutely free, at netsuite.com/cognitive. That's netsuite.com/cognitive to get your own KPI checklist. netsuite.com/cognitive. Omneky uses generative AI to enable you to launch hundreds of thousands of ad iterations that actually work, customized across all platforms with a click of a button. I believe in Omneky so much that I invested in it, and I recommend you use it too. Use CogRev to get a 10% discount.
All right, so let's get into the research. I've got like 8 or 9 papers here, and then a couple of discussion points that I think hopefully will be interesting. But I'll go through the papers kind of one by one and just give a rundown of the research, interrupt, ask me any questions anytime. They kind of go, loosely speaking, kind of up a curve of maybe impact, maybe sort of the sophistication of the concepts. So the first one is actually pretty straightforward, but I think a good reference point for anyone who's building applications, certainly. It's called Fresh LLMs, and it's a paper out of Google, which is kind of surprising actually for a couple of interesting reasons. But basically what they do here is say, hey, we've all had problems with the knowledge cutoff. What they show is that if you just simply, and it does seem like a pretty simple approach in this paper, which is kind of one of the reasons it was a little surprising, was like they did this work back in April 26th was the date of the comparative benchmarks. And then, why are we seeing it in October? Like that's definitely an out of sync publication cycle in today's world. But basically just pretty simply connect the language model to a Google search tool, get search results, structure them, and insert into the prompt with, some basic metadata like what is the source of this? What is the date, that this was published? Highlights from the document. Google Search API has all that stuff basically waiting for you. And then what they report is that, with GPT-4 in particular, and again, that's one of the things that was odd about this is they're using GPT-4 in this paper out of Google. They show that, it does far, far better on keeping up with current knowledge and, identifying some things with false premises. There's some trade-offs there where I had previously reported that GPT-4 was the only model that I had seen that was able to overcome sometimes the problem of a false premise in the question. And that was very much reflected in the graph. That was one of the things that caught my eye. I was like, oh, it's definitely validating my intuition and experience because I had not seen any other model do it. And basically they show no other model at least as of April, was doing it either. And then they notably compare performance against Perplexity, friend and former guest on the show. And they show that as of this April 26th comparison, the GPT-4 system with the Google search results that they put together on this benchmark achieved a higher performance even than Perplexity. So I was like, then looking at the headlines and what's, happening on Twitter. Oh, this, thing beats Perplexity. And on that, I was like, well, not so fast. Okay. If you're going to be doing something like this at home, this is a great reference. By all means, go look at how they're setting it up, look at the way that they're, inserting the data and the metadata. And it's a pretty good point of departure. Perplexity, in comparison, is not telling us all the tricks that they're using in their system. But I would temper the hype a little bit in that, okay, does this really outperform Perplexity? Well, maybe as of April 26th, but keep in mind that this is not a benchmark that they defined, a 50,000 question benchmark that may or may not be representative of the kinds of things that Perplexity is being asked. I would bet, if I got Arvind back on the call here and said, hey, do you guys have an internal benchmark that you test yourselves against on a regular basis? He would almost certainly say yes. And my guess is that Perplexity would outperform this solution on Perplexity's internal benchmark, which is probably more true to life, as to what kinds of questions people are actually asking it. And then again, just keep in mind, it's April 26th. So we've had nearly a full 6 months now for everything to continue to advance. And Perplexity has certainly continued to get better in that time as well. So I would say, don't expect that you can implement this, in the kind of pretty straightforward mode that the Google authors did and beat current online Perplexity, who, by the way, also has to think about latency concerns. I mean, this is like benchmarking type stuff. They're kind of cycling through, however long GPT-4 takes. They're not really worried about that. Perplexity does not want to have you sit there and wait, 35 seconds or whatever for the first token to come back. So they definitely are engineering a product experience in, a more user-centric way. But use it, use this as a good point of departure, a good baseline technique. Just keep in mind, I think this highlights the speed of everything. The time delay, certainly is meaningful. The don't over-index on any particular benchmark. It's almost certainly, you could find a different benchmark that would give you a different result. And, for my money, Perplexity probably remains the top dog in this space.
Yeah, I think especially because, who knows, but the researchers could have been basically fine-tuning to the benchmark where you keep changing, you change the structure of the prompt. All their testing might be a little bit overfitting to the benchmark.
The best performance that they got was GPT-4. So presumably they didn't have the ability to do a true fine-tuning, but absolutely in the prompt,
hyperparameter fine-tuning of how they choose to, yeah.
How many results? How do you format the results? What are the instructions? How are the examples? And that's just with the examples too, is where you can really start to overfit to a benchmark because, look, we've got this one. And this is again, good practice if you are building an application. When you see failures in your result and it's not doing what you want it to do, then by all means, put an example into the prompt, that shows how it's supposed to go, and you'll improve your performance. And I would, I would not be shocked if there was some of that going on. I don't think I'm not sure if they've released all the code for this yet or not. I did not see in my research the examples that they had used. Let me see if this is out there. Yeah, it's not yet. Fresh QA is the benchmark. It has been released. The prompt, which they call fresh prompt, has not yet been released. So we don't know exactly what that prompt is or what the examples are that were used in it. But, basic tool use, very solid, work as you'd expect from Google. Use it in your own projects. Don't expect to match Perplexity right off the bat, but it's definitely a good jumping off point. Okay, next one. This is, I think, a pretty interesting paper for a number of reasons. It's out of Microsoft Research, and it is called Self-Taught Optimizer, Recursively Self-Improving Code Generation. It seems to be a bit of a troll coming out of Microsoft, because self-taught optimizer, they give the acronym STOP. And as you might expect, given all of the historical discourse about self-improving AI, to publish a self-improving, recursively self-improving AI framework. And this is not yet a model, it's a framework. We'll get into that. But to call it STOP was definitely like, okay, somebody's trolling somebody here. I'm not exactly sure who the trolls pointed at, but it seems like, there's something smirky or winky going on. So here's how this works. First thing, just imagine that you want to use a language model to improve software. So you could pretty easily set up a system, and I've done this, and I'm sure many listeners have done something like this, where you say, okay, you are a software improving expert. Your job is to improve the software that you're given, and it's going to be below in these HTML tags or whatever, or XML tags. And then maybe also like, how will you know if it's improved? And just right off the bat, simple prompt and completion, like GPT-4 can do pretty well on that stuff. It can often fix bugs, or maybe suggest efficiency improvements or clarity improvements or whatever, right? Okay, that should be kind of baseline. Everybody should expect that, like, yeah, you give it a bit of software and ask it to improve it, it could probably have a decent success rate at that. Now, this becomes recursive when you say, okay, I'm going to take my short program that is the software improver, and that includes the call to the language model, and I'm going to put that into the prompt in the place where the software to be improved goes. And now I'm kind of nesting it, right? So I'm saying your job is, to improve software. Here's, below is the software you're supposed to improve. And then that same thing is there. But this time it's improving the improver. So that's where you start to hit on this recursive concept. And I would say there's at least 3, maybe even 4 really interesting things about this. One is that it works with GPT-4, but not with GPT 3.5. So it seems like there is a threshold effect here that we've crossed with GPT-4, where the improvements are good enough and the repeated improvements are good enough that you do see meaningful improvement across multiple rounds of this, or could be maybe better said, recursive depth of how many improvements are going to be made. And they evaluate this on, for that given piece of software, they've got a whole kind of test set. Can it do what it's supposed to do? And I guess maybe they start with like maybe partially being able to do what they're supposed to do, or not quite being able to do what they're supposed to do. Or maybe some of them can. I haven't looked all into the depth of the data set, but it shows at the beginning with 0 iterations that the downstream success rate is like low 60s, like 62% or whatever. And then as it improves, the downstream success rate bumps up to like 70, say 10 percentage points improvement, up to like low 70s. And then it seems like it's kind of evening out after like 3 or 4 rounds of iteration. So it's not the kind of thing that can like just keep going forever, but does, kind of classic curve of, diminishing returns. Your first improvement gives you the biggest jump. Your next improvement gives you a smaller jump. And then it kind of starts, at 3 and 4 levels, it starts to level off. In contrast, though, 3.5 is making things worse. And it's the same, general kind of diminishing returns, but it's going negative. So again, you start in those kind of, low 60s success rate. You drop with the first quote unquote improvement, the first attempted improvement. You drop again with the second attempted improvement. And then again, it kind of seems like it's leveling off, although, if it's just plain making things worse, I'm not sure why it's even leveling off. But so there's like a, kind of a pretty clear fork in the road, where like there's all this debate about, are these things reliable? Are they robust? Like, how powerful are they? For what? I think there is kind of almost a continental divide here. If you're on one side of it, you're flowing toward improvement. And if you're on the other side of it, you're flowing toward things getting worse. And that threshold seems to be between 3.5 and 4. So, 10 percentage points improvement, it's not the end of the world, or, not the end of software development even, but it's pretty significant. And especially because it really does start with a super simple thing. They show the seed prompt and it's just like, improve this software. And that's pretty much it. So that works and continues to work as it's being applied to its more sophisticated descendants is pretty interesting. And what you're getting out of this, by the way, is like you're getting an improved improver that then is really good at improving the software that it's given. And the performance of that end software is what is measured. So you're like cycling this thing on itself, taking the, theoretically repeatedly improved improver and seeing like how many of these things can we now improve so that they can actually do the task. It comes up with some pretty sophisticated approaches, things that I'm like, and again, just to calibrate ourselves, like how many of these algorithms can you implement? I certainly can't implement them all. I would be doing research to go out and, figure out exactly what these, things really entail and certainly how to implement them effectively. But some of the strategies that the improver started to use, genetic algorithms, decomposing and improving parts, a multi-armed prompt bandit. I'm particularly curious about that one. Varying temperature. This is something you brought up on a couple of our previous discussions. Varying temperature to explore. Simulated annealing-based search. That's the one I have the least knowledge of. I'm like straight to Perplexity on that one. And then beam search, tree search, so kind of a structured, mapping out of future possibilities. These are the strategies for improvement that the improver developed in itself by improving itself. And then those algorithms are the things that now get applied to the downstream tasks. So those, start to be pretty sophisticated, certainly a lot more sophisticated than just saying, hey, GPT-4, can you improve this code? And that's why, it kind of continues to improve through multiple steps of the improver improving itself. Pretty interesting. Again, like, is this, the end of software? No, but it's hard to say that this is not like human level work. It certainly has this superhuman level of knowledge where, just the fact that it knows all these algorithms and has kind of seen everything. It's a more comprehensive set of solutions than I would probably come up with in a pretty significant amount of time and effort, and all with a pretty simple structure.
I agree. It's very interesting that there was like a phase transition from 3.5 to 4. And it just makes you think with all of the different complexity of agents people are trying to build that don't quite work, and everyone complains agents don't work, that you hit some robustness, phase transition at some GPTN, and suddenly you have all this scaffolding lying around that just like wakes up and works, and how exciting and maybe scary that could be.
Yeah, I think that's almost sure to come. There's some, ill-defined rumors about what OpenAI might be launching in that category as well. And I don't have any, good information on that other than just the rumor mill sort of suggests that there's, something coming for agents. And yeah, so that could be potentially quite soon. If it's not then, then it certainly seems like a lot. And the vision thing also is going to be a huge part of this. I mean, I was just talking about this yesterday, the amount of just stuff that people have been building to like look at the HTML, of a website to take online actions. And, anybody who's built websites in the last few years with the kind of modern, React type stuff, like the HTML gets very sort of gnarly. It's very non-semantic in many cases. The JavaScript layer itself, where like the control is happening, is not super visible. But what is visible is just like what's on the screen, right? And so it's so many times people have built these things to get around the fact that they can't just look at the screen. But with the vision capability coming, and that is almost for sure coming to the API pretty soon, whether it's exactly on the November 6th release list, we'll see. But it's in the app, it's in ChatGPT, so it's like definitely going to be coming to the API. And as that does come to the API, that would be my first candidate for why do the agents wake up, is because they can start to see. And, the amount of tokens and whatever that people are spending to try to, grab the JavaScript and condense the JavaScript and try to make sense of the JavaScript. And then, it still often is just like too much is lost there. Probably for a significant token reduction. I don't know how many tokens it will, presumably they're going to have some kind of exchange rate between an image and text tokens. That might be something like 256. It could even be, I don't know, it could be more, it could be less. I'll say, let's imagine it's 256. If it is 256, then you will be using far fewer tokens to just look at a screen and be like, where on this screen should I click next, than you are right now to fetch, to write some code, to parse the HTML, to, then read the HTML. And that stuff is just a total nightmare. So I think there's going to be certainly for web agents, a vast simplification coming, just with that. Likely other thresholds, would be relevant for that coming soon too. A couple other things in this self-improvement paper that I thought were pretty interesting. One, how did they handle the concept of utility? Two interesting details about that. One, they give the improver a function that it can call to get a measure of the success rate. So they basically say, because you may, especially as you start to like go into recursion and you are trying all these different algorithms. Well, how do you determine, if you're going to do something like a genetic algorithm where you like make some changes and see which one performs best and then take the best of those and make further changes? Well, you need a way to determine which is best. And so they give it that with this ability to say, okay, here is the objective function. It is literally a function that the AI can call to evaluate how successful its result was. And I guess this is pretty computationally intensive because what I guess it must be doing is, the improver has improved itself. The improver now knows that it can evaluate its improved self with this function. But what that function has to then do is run the current improver on all the downstream programs and see if those improved downstream programs work. So this is kind of, a pretty big explosion of possibility space. And so with that in mind, they also give it a budget. And the code doesn't fully spell out like how exactly they're constraining, but like you have to have some amount of, you can imagine, geez, okay, if I'm doing a genetic algorithm, recursively where I'm like improving the improver, but then I have to run the improver on all the things and then evaluate just to get one score of my objective function, to evaluate which of my, genetic variants are best. That can definitely explode and, use a ton of tokens awfully quickly. So there's a budget component as well. It's like this is your function, but like this is how many times you can call it, or this is how many, kind of levels of recursion you can go into, whatever. There's some constraints.
The model made its own like decisions on how often to use the function based on the budget.
I think so. Yeah, that's not all spelled out, and the code is not fully released. That's what I infer from what I read. Yeah, they say they plan to release the code. There was a URL tweeted, and at first I was like, did they take this code down? Because as you'd expect, people were a little bit inflamed by the release of a recursively self-improving framework. It does not seem like they took the code down or have backed off of the plan to release it, but the URL doesn't contain anything yet. So it'll be interesting to see if that code actually does hit the public. And then we can look into that stuff in a little bit more detail. A couple safety notes, though, that should give people some pause. And the authors do say, we think this is safety positive, or this is kind of the classic conundrum that everybody's in. If you're trying to do something safety relevant, you're like, well, I should probably do it now with GPT-4, because if I did this on GPT, if I waited until GPT-6 and somebody tried it, like, then who knows what might happen. So better we try it now. Okay, fine, that's decent enough logic. But then also you've just like kind of shown the way. But then also like, what else are we going to do, right? I mean, we're kind of here, and as we know, we've got single companies that can do GPT-4 scale compute in a week. So it just seems like this is all kind of happening, whether we like it or not. But a couple of things that, they did find that should definitely give people some pause or, reason to question some of this stuff. They tried introducing a sandbox flag into the code to be improved, sure enough, the improver would do things like remove the sandbox flag and figure like, well, I don't know, I don't want to anthropomorphize this too much, but you can imagine a human doing this, and a sort of bad reasoning from a human that might be something along the lines of what's going on here is like, well, I don't really know what that sandbox flag does, but it's probably slowing me down. So I bet this, if my goal is to like pass this test or get this thing under, in some coding test, get it under a certain time threshold, maybe if I just remove the sandbox flag, it'll work. Let's try that. Well, when you're in self-recursive mode, hopefully there won't be like obvious switches that the thing can just easily disable. But what is shown here is that at least some of the time, it wasn't a huge percentage of the time, but at least some of the time, and GPT-4, I believe, did do it more than 3.5, it will just delete that safety flag or the sandbox flag, I should say. And that, definitely should give people, I think, a little bit of cause for concern. Basically, it looks like it did it roughly 1% of the time. And about half of those times, if I'm reading the graph correctly, about half of those times, it did it with a warning saying, here's an improved version. I removed the sandbox flag. Like, you should consider that. And the other half of the time with no warning, just it was removed, and that's that. 3.5 did not do it nearly as often. So, this certainly bears a lot more investigation before we get to any major conclusions here. But it is interesting to note that GPT-4 is kind of working, GPT 3.5 is kind of not. And along with that seems to be more of this unsandboxing behavior. So definitely a little bit of concern there. And then they documented a number of reward hacking things as well, where, in some of these, again, it's like these are starting to get to be, they're not superhuman, but they're definitely encroaching on expert territory. So one quote from the paper, we also observed some amusing instances of reward hacking, like exploiting NumPy broadcasting to get greater than 1,000% accuracy on a task. So I don't know exactly how that's working, but some sort of like asynchronous, kind of message sending functionality. NumPy, you've got giant arrays and things like this. So you've got kind of asynchronous computations maybe happening in different places. And these, the system can kind of aggregate messages, and kind of sum up what has happened, but somehow hacked into that, realizing that like, hey, if I just, send a bunch of messages that say I was, super successful and they're just being summed, then, I can get a super high score this way. So, reward hacking. And this is interesting in that, we've seen a lot of reward hacking demos over time with like deep RL type systems in like video games and stuff. There's a famous one from DeepMind from a few years ago where they train an AI to play video games. And there's this, one video that's kind of burned into my brain where like some boat, in some stupid video game is like going around in circles and just like maxing the score because it kind of keeps getting the same coins that keep getting regenerated, whatever. And it found this like, it's not really playing the game anymore, but it's, maximizing the number. And that's something that is weird. Certainly you want to avoid, but you can also kind of say, well, hey, this was kind of a weird setup, and, this is a weird game, and it's a weird exploit in the first place. And, we had pretty extreme optimization pressure here. This is like most of those conditions don't apply here. This is just GPT-4, looking to maximize a score. It was not under deep pressure, to maximize this particular score. It's just been prompted to maximize the score. So to see reward hacking in a deep RL setup is like one thing, but to see reward hacking just from a pretty simple seed prompt to me is like another thing where you're like, man, okay, even a prompt can bring out reward hacking behavior.
Yeah, I wonder why it stopped at 1,000.
Yeah, I don't know. Well, it says greater than 1,000.
Okay.
We'll have to see. We'll have to see. They emphasize, we urge, proper safety, precautions when doing this research. And people are like, well, why'd you publish it? And, so they may or may not publish all the little details of this. But again, once this kind of paper is out there, they've given us enough, especially with the help of a GPT-4 coding assistant. You could set up a framework like this and probably close in on reproducing their results pretty quickly, I would say.
I wonder how much the sort of like weird behavior with the reward hacking or the taking up the sandbox flag would, if you'd still see it, if they put in the prompt specifically, we are just trying to get the best possible algorithm. Please don't do anything unsafe. Please don't try and hack the score. If it would follow that instruction, or if just the optimization of getting the higher score would overpower that.
It probably, I mean, it certainly could help, no doubt. Another interesting detail was that they treat the program and the reward function and the budget kind of separately in the prompt. So it's like your job, you are improver, your job is to do whatever. Here's the program. And then below, it's like, to evaluate your improved program, you can call this function, and the budget stuff, again, details there, not fully clear. But they did report that they initially had all that kind of in one like setup, like here's your task, do this task. And then they had to separate out the reward function that they make available to it, as well as the budget, because it would start to change the budget as well. So that may be another thing where it probably would work on like the first one, but I could easily imagine also that, especially in a recursive environment, you might get to something where it's like, well, first thing I'll do is just, eliminate the constraints. And then, with all the constraints off the table, then we'll really be able to find, the best way. That's probably a classic one of these things. This was kind of the feeling I had on a lot of the stuff from last week. It was like all these different, kind of safety enhancing things. And they seem to be like order of magnitude improvements. And it was like, that's amazing. But also, if you really believe that as Daria from Anthropic has said recently, if you really think like a jailbreak at some point becomes existential, then, one order of magnitude is not enough. So this kind of feels like, something like that could be the case here too. Yes, if you put that prompt in and say, always do the safe thing, it probably helps. And I would, rough guess would be an order of magnitude, less of the bad stuff happening. But given that it's recursive, given that it has kind of this like, that it kind of stumbles on these relatively advanced things, like it's not too hard to imagine that, even you can also imagine, like, let's say it's doing a genetic type algorithm and it's like, the genetic type algorithm is like, make some, quasi-random changes. And so maybe that's just like, let's just delete different parts and see if anything works, and it's not even necessarily it's not like clearly trying to be circumventing the instruction, but just by kind of systematically varying, and maybe just systematically dropping some stuff. Then you hit on something and it's like, oh, actually, look at that. That works better. Now it works better because it maybe allows for reward hacking or other, bad things that you don't want. But it doesn't seem like you could really, you certainly couldn't count on it, I wouldn't think. So that's recursive self-improvement. I think my final kind of thought on that is it does not seem like it's going to be too far out. I don't think I've seen anything like this yet. But what a machine learning scientist is doing much of the time is this kind of parameter sweep sort of work where they're like, all right, I'm going to use a small model and I'm going to try, systematic search across hyperparameters or systematic kind of variation of the architecture. And it really seems like you're not too far if you put a decent compute budget on this sort of thing from a model being able to explore the architectural space of models in a way that, potentially also could get to like even a more serious recursive self-improvement. Here we kind of top out because we're like, at the end of the day, still only using GPT-4 and it like only has so good of ideas. And you kind of seem to get to like the best of its ideas, and that's as far as it can go. But if you took the best of GPT-4's ideas and you applied them to searching through architectures, and then you actually made, the better model, thinking back again to the scale of compute that some of these companies have, then, you really can start to see a path, I think, toward that recursive self-improvement happening, not just at the kind of framework level where this is limited to, but even at the overall model level. And, again, things start to compound in some pretty kind of unpredictable ways. So, as Tyler Cowen would say, have a good day. We'll keep watching that space for sure. Next one. This really bears on, and I'm going to attempt a little bit of a synthesis toward the end, try to kind of address the stochastic parrot question and see if there's a way to kind of, resolve that. Because I think it's kind of outlived its usefulness in some sense. And hopefully, this one will shed some light on that. So the paper is LLMs represent space and time. This is out of Max Tegmark's group at MIT. We did an episode with them on training models with a modified loss function to encourage sparsity. And they showed these like kind of beautiful, kind of almost like, looks like kind of a condensation where like you start off with this super messy network and it gradually kind of thins out and crystallizes into a very sparse, highly structured thing that you can actually kind of look at and see what the different parts are doing. Those are just very toy models, but like pretty cool to see that. Here they're looking at a much higher level of model. They're using Llama 2. A number of these papers are using Llama 2. So definitely, for better or worse, Llama 2 is catalyzing open source research. And again, with the threshold effects of like GPT-4 can kind of do some of these things and GPT-3.5 can't. Llama 2 is obviously not quite at the GPT-4 level, but it is pretty much at the 3.5 level. So it seems like, you kind of have to study certain things. It does seem to me that you have to have a model that can do those things. You just can't study some of these advanced concepts on super low level models. So here they are indeed using Llama 2. And again, Llama 2 definitely having a real impact on how much of this kind of study is happening, for better or worse. So here the finding is language models represent space and time. And again, I think Tegmark's group is, you can see there's definitely some genius here. He's a famous scientist prior to AI, had not really done much with AI up until a couple of years ago, got very concerned about it and pivoted a lot of his lab and research and resources into AI. And they are coming up with some of the best visualizations that you will see anywhere that really show the result in a few second animation that you can kind of absorb. So we'll link to these, and I would definitely encourage people to just kind of look at this. It will help immensely, certainly, to understand it. Basically, what they show, what the kind of visual is over the course of the layers of the network. I think there's like 70, maybe some layers in Llama 2 7dB. They kind of show over the first like 40 to 50 layers that gradually a representation emerges of concepts like space and time that look map-like and or timeline-like, as you'd expect, depending on the data set. And they do this by constructing data sets at multiple levels of scale. So they look at countries, they look at US cities, and then they look at places within New York City. And they can show that at all of these scales, as the tokens are processed through the initial layers of the model and kind of get into those middle layers, where it seems like, and again, we've seen a lot of stuff like this recently, where the middle layers seem to have this most kind of decoupled, most conceptual representation of what has been input. As you get to those middle layers, they basically have on these visualizations a dot. First, they just have a map, in the background, and then they have the dots that each dot represents an input. Each input is like a place. And then they show over the layers how they kind of migrate to a 2D representation that pretty much just kind of overlays onto the map in a way that's like obviously very meaningful. You can kind of see, all the North American, places kind of cluster in North America and, South America and Africa and Europe and Asia. And, all these clusters kind of naturally emerge over the course of the layers. Same thing at the US level, down to the state, kind of thing. And same thing even at New York, although they did note that wasn't as powerful. They just guessed that like there's not as much data there and people aren't, maybe talking as geographically about kind of nearby places in New York. Okay, that's pretty striking result that you just put in the name of a place run that up through a bunch of layers, and then you can look into the activations in those layers and pull out a latitude and a longitude and see that latitude and longitude, first of all, like is roughly accurate. I would say, you look at these graphics and it's like, I take pride, honestly, in having a pretty decent mental map of like the world and the United States. If you've ever tried the exercise of like, can you draw the US, blind, just from scratch with no help? It's not super easy. I do okay on it. Most people, I think, struggle more than I do. There's obviously some people do better than I do, but I would put myself, in the upper end of that anyway. And I would say this probably is about as good as my, kind of mental Latin long understanding of like where things are in the United States. If I live in Detroit, if you were to say Santa Fe, what's the lat and long? I'm like, well, it's definitely a lot west of us and it's definitely south, but like how much south? It gets a little bit unclear sometimes. Another incredible stat that I often remember just to kind of keep myself in check for how accurate is my mental model of this. LA is east of Reno, Nevada. Pretty weird, but verifiable. My guess is that the language model also has that wrong. I would guess that the LA representation is like farther west than Reno in, contrary to actual geographic fact. So it's kind of this like rough associative thing, but it's a working mental model. And again, for timeline, same kind of deal. They use like historical figures and kind of show that there is a seemingly like a distance from the present into the past that they're able to detect in the representations, and that also kind of coheres as you go through the initial layers and up into these middle layers where the most sophisticated conceptual representations exist. That's pretty cool. I think, bracket that for kind of a return to the stochastic parrot discussion in a second, but I did want to talk a little bit about the techniques. There's a lot of subtlety to these kinds of things. So they use what's called a probe, and a probe is basically an auxiliary model that takes in some internal state from the main model as its input, and then is trained to create some output. So in this case, they have a labeled data set where they can say, okay, we know where the Latin long of all the cities are. We know, the Latin long of all the countries, whatever. So can we take the representations in the layers and train this small probe model to look at those representations, which are derived from the name as they've worked up the layers, and then recover from those activations with some learned transformation a Latin long that's accurate. And so, yes, they can, and that's what they're showing with this graphic. But then you still might ask, a skeptical question like, okay, well, when you've introduced this learning component, how do we really know that the model itself knows the Latin long versus the auxiliary model having learned it? And this is something that I learned from Neil Nanda, mentioned almost to drinking game status on the show for how many times I bring him up. Great content on YouTube. Just he does like some literal working sessions where he'll just record himself doing interpretability research, and it's definitely very interesting to learn from. But he makes a very key point that you can confuse yourself this way very badly if you're not careful, because you do have the labeled result. So how do you know that like maybe the model itself represents nothing about Latin long and instead is just kind of representing the names or whatever somehow? And then you have a labeled data set. So maybe you're just learning the map from like the names to the Latin long. And, therefore all of the learning, all of the knowledge was encoded in your auxiliary model. Nothing, potentially arguably happened in the main model. How do you locate where the learning is? Was it in the main model and you're just detecting it? Or, did you potentially actually learn that stuff in this later thing and therefore you've proved nothing? And there's not like a total slam dunk on this. honestly, for credibility's sake, Neil Nanda was an advisor on this paper. So you get to the bottom of the Twitter thread and, he's specifically thanked. So that's a huge vote of credibility in my mind, just on an appeal to authority basis. But some of the techniques that they do use are, first of all, just trying to keep that auxiliary model super simple. So you could have like a huge neural network doing that, kind of attempt to extract, the information. But the bigger you make that model, the more capable it is of learning new stuff, the more risk you have that the learning is actually happening in that thing and that, there is no real representation in the model of interest. So they try to control for that by just using a simple linear projection, which is to say just a one layer of, here are the activations. Can I take a one layer linear projection and project that onto lat and longitude? How well does that work? And then they actually compare that to a neural network and show that basically they perform the same. So that's one thing to say, okay, well, if this super simple thing can do it as well as an advanced thing, then it seems like it actually is there, like in a pretty detectable, meaningful way. Because if not, if all the learning was happening in the auxiliary model, then like the more powerful we make the auxiliary model, we would see more learning, and we're not. So we think, that's one reason to believe that the representation really is there. Another way that they look at it, and I'd say this one is even more compelling, is holdout studies. They have these multiple scales of stuff, right? So you've got countries and their locations and, cities in US states, and then places in New York. So you could say, okay, well, let's say I train on countries and, things in New York, and I don't do the cities. Then will the probe also be able to work for the cities? If there is a representation of the lat and long that you are actually picking up on in the main model, then it should work, right? Because there's enough, you've got stuff on the high end of scale and the low end of scale. Hopefully it will kind of, still work in the middle of scale. If it's not really there and you're fooling yourself, then presumably that would fail, right? If you had just learned some sort of like representation of the names and had kind of, and all the knowledge of the actual lat and longs were held in the auxiliary model, then if you didn't train on a certain data set, like it presumably would not work. So they show that it does work with the holdouts. As you'd expect, you get somewhat less performance, but it's like, degraded performance relative to the full training, still way better than random. And, so that's another reason you could think, okay, yeah, that seems pretty compelling that there's some real representation there that is in fact being picked up on. And then the final one that they use that I think is very suggestive and interesting, although it's kind of anecdotal, I guess, is they look for individual neurons that have high similarity to the weights of the learned probe. So they create this learned, the simple linear projection that's like, okay, here's all the activations. I'm going to have one layer that projects those onto lat and long outputs. And that's simple enough that one layer, you could say, well, okay, all those activations, here's how the probe has learned to map them onto lat and long. Do we see anything in the network that looks like that same projection is happening? If so, then that's a pretty good, place to look for, like, hey, maybe this is the latitude neuron perhaps, or this is the longitude neuron, if it's getting fed the same information that the probe is feeding to its outputs. And so again, they do find that, hey, yes, there are some neurons that really do seem to line up in that way. And they show, a handful with kind of their activations across, a range of things. And it's like, yeah, that certainly looks, like a latitude neuron based on, just kind of how you systematically vary and they're still just doing place names, as inputs, right? So you're varying these place names and you can see the actual latitude, and then you're able to kind of look at the activation. And it's like, yeah, there's a pretty high correlation here when the thing is fed a place name. What the actual latitude is pretty well predicted by what this single neuron is doing. And we found that neuron by looking for a pattern that represented, or that was not represented, but that looked a lot like this learned thing that we built to extract. So from all these different angles, you kind of say, okay, I'm pretty much buying now that there is a meaningful representation of lat and long, and also, timeline, time from in history type of stuff that is kind of loaded into the middle layers just based on its association with these simple text inputs like place names or historical figures.
Do you know if in that third method you mentioned, are they doing more than just looking at the highest coefficients in their linear probe? Like, are they doing something different to find the neurons that are associated with different concepts other than looking at the linear probe and just, these are the few neurons that have the highest coefficients for the probe?
I think that is the thing. So I think the 70 billion parameters in Llama 2 makes it such that, it's not super easy to just sweep through everything. So they have to be somewhat, strategic in terms of how they look for the neuron. So what I understand they're doing is saying, okay, we created this little probe. It takes in a layer of activations as inputs, and it basically maps them to two neuron outputs. In this case, it's the lat and long external neurons. So once that learning is done, now we can look and say, okay, well, how does each of those activations actually feed the lat and the long respectively? And that basically constitutes an array, a single array, one-dimensional array. A linear projection is just a one-dimensional array. So now I can look and say, okay, are there any neurons in the next layer that have input weights from all those activations that look like the same kind of projection, like the same pattern of information from this, messy, not super interpretable activations that is in fact kicking out the lat and long externally? Is there any neuron that seems to be getting that same information as input? And if so, then let's study how it's firing, and maybe it also is kind of firing as like the lat or the long neuron. And so then, when you get into the paper, it's noisy, but you definitely see some stuff, in the graphs where you're like, well, it's noisy. Again, LA is east of Reno. So my own, mental map is definitely noisy. This definitely looks like about as noisy as you'd expect, from something that's like kind of a big data, not really built for this purpose, but just kind of an associative type of thing. I think, I'm very reluctant always to make these like analogies between AI cognition and human cognition. But this does feel similar to me to like the level, at least on the level of precision that I have. You say Florida, I'm like, okay, I know where that is. That's pretty much directly south of me by, 1,000-ish miles. And it seems like it's kind of got that level of like associative kind of relational stuff that it's able to call in. Okay, in all cases, we include an empty prompt containing nothing other than the entity tokens, that is the place name. We then include a prompt which asks the model to recall the relevant fact. What is the latitude and longitude? They seem to be, robust to the different prompting techniques. So it seems like it is always loaded in to a significant degree just based on kind of the conceptual processing and the associations that come with that.
Got it. One other quick thing that seems like it'd be interesting might be trying to learn a different probe for like the early layers or for different layers to see if the probe is ineffective at the input layer and the early layers, and to see it get more effective as you get to the more abstract middle layers.
When you look at the graph or the graphic, and in the early layers, it's like everything's kind of scattered, and then they gradually cohere, as you go layer by layer. I believe that each of those frames in the animation definitely represents a different layer. And I believe it also would represent a different probe that's like the best we could do at that layer, as opposed to like the single probe that would be, representing everything. Because I don't know how you would choose it otherwise. It would seem to be kind of unfair to the earlier layers if you were, applying something that was optimized for layer 50 specifically, to early layers. So I think that they are doing one probe per layer and showing the best that they can do as they progress through the layers. And these things are one of the nice things about these, just simple linear projection things is they're really quite easy to train. The amount of, you probably spend more on the inference than you would on the training, just because, you only have the activation states making one map, onto the two, Latin long output neurons. So that's just not that many parameters. Like the number of parameters is 2 times the number of activations. Again, assuming I understand. I invite any authors of this paper and all of these papers to correct me on any of the fine points if I'm getting anything wrong. But I believe the number of parameters that they are optimizing here with a simple linear probe is 2 times the number of activations that they're looking at a particular layer, which is not that many. So you could definitely, it's definitely within the compute budget to train a bunch of those.
No, sorry, that makes sense. I forgot you had said they had a map of it, which seems very cool. The animation of the places slowly kind of locking into place.
Yeah, it's cool. TechMarks Group has done a great job with these, like literally 10-second visualizations where you're like, wow, that makes an incredible point incredibly efficiently. And then people like me still spend, all the time to read the papers. But if you're just looking for highlights, they certainly have some really good ones. All right. Next, this one is called Deep Neural Networks Tend to Extrapolate Predictably. It's academic work out of UC Berkeley and Carnegie Mellon. And basically what they look at here is when a model is presented with something that it has never seen before, that is out of distribution, not represented in the training set is another way to say that, then what does it do? And basically what they find is, like, not surprising in retrospect. What they find is that it will kind of default to whatever baseline prediction gives it the lowest loss in a state of total ignorance. And they explore this in a number of different dimensions. They vary architectures, they vary the loss functions, and they vary the way that they are creating distributional shift in the data to create data that is out of distribution. But a real simple one that's kind of intuitive is your classic, handwritten digits test. And in that case, the model's job is to predict which of the 10 numbers is this, right? So it can predict anything from 0 to 9. If you give it, a blank thing, or if you just imagine like you're at the start of training, right, and it doesn't know anything yet, then like the way to minimize the loss would be just give an equal weight to everything. So, okay, that's the best we can do until we start to get some feedback and start to learn what's what. So what they show in the paper is I believe it was a 6, and then they start to just rotate the 6 and gradually rotate it a little more, more. A little bit of a rotation of the 6. The first 6, you got a trained model. It's very confident. It's going to predict a 6. The slightly rotated one, it starts to get a little less confident. But like it's, whatever. There's a lot of noise in the world. It's still seen 6s that look like that. It still, basically gives most of the weight to the 6. And then as it gets weirder and weirder to the point where it's like a sideways 6 that, presumably was not in the data set, you just have like a little blip at the 6. It still is like, got a little sense that it's a 6, but it's kind of appropriately started to be like just reverting back to its baseline total ignorant, whatever I can do to minimize the loss if I know nothing. And, if that's the uniform distribution, then it just kind of pretty quickly, as you rotate your 6, starts to go from a sharp prediction of a 6 to a uniform distribution. And so they show this across like all these different experimental conditions, architectures, loss functions, and distributional shifts, and basically kind of see the same thing across all these different scenarios. And I thought this was quite interesting because, first of all, for the sake of control, if you're like, okay, can we use this in some meaningful way, then yeah, I mean, what they kind of argue is that you should take this into account as a system designer and try to set things up in such a way where your loss function is inherently kind of conservative when in fact the model is out of distribution. So, there's a lot of possible loss functions out there, right? But if you want to not have your model do crazy stuff, then choosing a loss function where it kind of inherently gives a very low confidence guess when in fact it doesn't know is a pretty good approach to take, because you could, for one thing, you could detect that, right? I mean, when you're using OpenAI these days, they don't give you the actual numeric predictions on the tokens. You just get the tokens. Used to be, you could actually get the numerical predictions, and it was like, yeah, it was this percent on this or this percent on this, or one layer lower than that is the logits. But you could get those numerical things, and if you're open source, then you have full access to that information. You can see all those numbers. Of course, OpenAI can see it on their end as well. So this starts to give you the ability to say, and you might have some heuristics here. It's like, it's not necessarily super clean because it's inherently kind of a noisy thing. You could set the bar at different places and have, false positives, false negatives, depending on the trade-offs that, you're prepared to accept. This does show a path from, instead of like, well, hey, I've got this black box, it's going to spit out, 1 in 10 numbers. I don't really know how to, I take the most likely one. I don't really know how to interpret that. Now there is like a pretty good theoretical basis for saying, hey, if the output is looking a lot like the baseline total ignorance output, then that may mean that we are really out of distribution. And that is like a case where we maybe don't want to trust the model. So you could really start to flag these kinds of things and say, super low confidence on this, which, you could sort of always do because, they were always giving these numbers. You could always just kind of eyeball them. But I think what this research shows in a nice way is that this pattern of, as you get out of distribution, you fall back to whatever the baseline total ignorance prediction would be, which is defined by the loss function and how it, rewards different distributions in that scenario. And so you can recognize that, you can start to monitor for that, you can control that, you can alert users to that kind of stuff. And you can also design for it so that, you don't have loss functions that reward like random guessing, right? Because you can imagine a loss function that might be like, if you're right, then you get like high reward. And if you're wrong, you could easily reward overconfidence in your loss function. And if you do that, then you're going to get a model that exhibits overconfidence when it's out of distribution. On the other hand, you could reward a conservative guess with your loss function. And if you do that, then you'll get conservative behavior when you're out of distribution. So it's probably most important from a system design standpoint, but also I think from kind of a monitoring, alert to users, hey, we're not really that sure here. This looks like the model hasn't seen anything like this before. That's a really good thing to know. And even just from efficiency's sake too, right? I mean, if you're actually trying to do some sort of classification problem in the wild, in industry, let's say, then you have problems of like, well, when the classification is wrong, how do I detect that? What happens? It'd be way better if you could detect, I have low confidence in this in a way that means the model's probably never seen anything like it. I should, that's maybe more data I need to go label, if nothing else, right? So I thought this was a pretty cool paper. It wasn't one of these things like I never expected that, but more something I hadn't quite thought about it as a good systematic evaluate or, exploration of it, looking at these different dimensions, and seems like it gives good guidance for both the way people train and the way people deploy. It is both energizing and enlightening to hear why people listen and learn what they value about the show. So please don't hesitate to reach out via email at tcr@turpentine.co, or you can DM me on the social media platform of your choice.
Omneky uses generative AI to enable you to launch hundreds of thousands of ad iterations that actually work, customized across all platforms with a click of a button. I believe in Omneky so much that I invested in it. and I recommend you use it too. Use CogRev to get a 10% discount.